Hello everyone, welcome to one more lecture on fundamentals of logic. So in this lecture video we'll be discussing about methods of proof and methods of disproof, and also the types of proofs and disproofs and problems based on the proofs and disproofs. So we'll see one by one. The first one is direct proof. So this direct proof contains mainly three steps. First one is hypothesis, second is analysis, and third one is conclusion. So in the hypothesis step, first we have to assume that the proposition P is true. And step 2 is analysis. So here, starting with the hypothesis that P is true, and I'm going to employ few rules of inference and laws of logic and other known facts to infer that Q is true. And I'm going to conclude like if P, then Q is a true statement. This is called direct proof. Second one is indirect proof. So in this indirect proof, we know that a conditional statement if P then Q and a contrapositive statements if negation Q then negation P is logically equivalent. So in some situation, given a conditional if P then Q, a direct proof of the contrapositive one, negation Q and negation P is easier. So I'm going to prove the direct proof of the contrapositive statement that is negation Q and negation P, and I'm going to conclude like if P then Q is a true statement. So this method of proving a conditional is called an indirect method of proof. Next one is proof by contradiction. So same thing here also, I'll be taking three steps. First one is hypothesis, second one is analysis, third one is conclusion. So in the hypothesis step, I'm going to assume that if P then Q is a false statement. So if P then Q is a false means we must have P is true and Q is false. Analysis, starting with the hypothesis that Q is false and employing the rules of logics and the other known facts, this infer that P is false. So this P is a false is a contradiction for the assumption that P is true here. So I'm going to conclude like because of the contradiction we got in the analysis, we can infer that if P then Q is a true statement. So next one is proof by exemption. So first I'm going to recall the proposition of the form for all x belongs to S, P of x is true if P of x is true for every x in S. So if S consists of only a limited number of elements, so that we can prove that the statement for all x belongs to S, P of x is true by taking the statement that P of A for each A in the universe S and verifying that P of A is true in each cases. So such method of proof is called the method of exertion. So next one is disprove by counterexample. The way of disproving a proposition involving the universal quantifiers is to exhibit just one case where the proposition is false. So this method of disproof is called disproof by counterexample. So we'll see some examples for proof and disproofs. So first give a direct proof, indirect proof. Third one is proof by contradiction for the following statement. If n is an odd integer, then n plus 9 is an even integer. So we have to prove this statement in terms of direct proof, indirect proof and proof by contradiction. So we'll see one by one. First let me explain in terms of direct proof. Assume that n is an odd integer. Okay, the given statement actually what? N is an odd integer. So now I should prove n plus 9 is an even integer. So assume that n is an odd integer. So then n is equal to 2 plus k. So n is equal to 2 plus k is obviously it is an odd integer for some integer k. For example, if I replace k is equal to 0, k is equal to 1, k is equal to 2 and so on, I'll be getting odd number only. So hence I can say n is equal to 2k plus 1 is an odd integer. This gives n plus 9 is equal to what? 2k plus 1 plus 9. I'll be getting 2k plus 10. So I can take two common factor. I'll be getting 2 times of k plus 5. So from which it is evident that n plus 9 is an even integer, because you can see here, if I replace k is equal to 0, 1, 2, 3, 4, I'll be getting n plus 9 is equal to some even number only. So hence I can say that n plus 9 is an even integer. So this established that truth of the given statement by direct proof. So hence I got when n is an odd integer, I got n plus 9 is an even integer. Next is indirect proof. So assume that n plus 9 is not an even integer. Okay, I'm going to assume that n plus 9 is not an even integer. Then n plus 9 must be 2k plus 1. That is n plus 9 must be an odd integer for some integer k. Okay, this gives that n is equal to 2k plus 1 minus 10. I'm shifting this 9 to RHS. So I'll be getting what? N is equal to 2k plus 1 minus 9. I'll be getting 2k minus 8. By taking 2 common factor, I'll be getting 2 times of k minus 4. So which shows that n is an even. Thus, if n plus 9 is not an even, then n is not an odd number. Right? So this proves that the contrapositive of the given statement, because in the given statement the statement is given like n is an odd integer and we have to prove n plus 9 is an even integer. Here I took like n plus 9 is an even integer, then I got n is an even integer, then obviously it is true that n is not an odd number, right? So this proves a contrapositive of this given statement. So this proof of the contrapositive serves as an indirect proof of the given statement. Third one, proof by contradiction. Assume that the given statement is a false one. Okay, so that is, assume that n is an odd and n plus 9 is an odd number. Okay, so if n plus 9 is an odd number, in the sense I must have n plus 9 is equal to 2k plus 1, right, for some integer k. So that n will be equal to what? 2k plus 1 minus 9, then n will be 2 times of k minus 4 I will be getting, which shows that n is an even number. So but in the assumption I took like n is an odd number. So this is a contradiction for the given assumption that n is an odd number. Hence we can conclude that the given statement must be a true one. This is called proof by contradiction. Problem number 2, prove or disprove that the sum of square of any 4 non-zero integers is an even integer. Solution. So first I am going to take the propositions that for any 4 non-zero integers a, b, c, d, and a square plus b square plus c square plus d square is an even integer. So now I want to prove or disprove this statement. So we check that for a is equal to 1, b is equal to 1, c is equal to 1, d is equal to 2. The proposition is obviously false here, right? So thus the given proposition is not true proposition. So hence I can conclude that this proposition is disproved through the counter example of a is equal to, b is equal to, c is equal to 1 and d is equal to 2. Thank you.